So these are the fundamental laws that guide all heat transfers and energy transfers in general. But more usefully, we need to look into the how rather than the why. So back to the stuff really that you've kind of looked at in Key Stage 3 and Key Stage 4, which is actually looking at how heat itself transfers. Now, you've obviously know about conduction, convection, and radiation for the exams, but there are more than those mechanisms. Effectively, they've got to fall though into those two ways that energy can transfer. It's either work done by forces pushing things around, or it's photons being emitted. So evaporation, diffusion are just as powerful ways of moving heat around as others. Evaporation is a big thing. Biology is based on these two systems. So evaporation is big. The whole thing about it is that particles that are going fast enough can jump out of a liquid, but only if they've got enough energy due to collisions. So when they're hit, they can be literally knocked out of the substance. Okay, they have enough energy to overcome the bonding energy. Which means that if those higher energy ones have gone, the ones that are moving slower, the ones left behind, are going to be much lower energy, therefore the actual temperature of the liquid is lower. Okay, so as it says here, sweating, that's the main way that actual animals are cooled down due to this sweating process. Now, if they jump out, they can hang around, they might not have much energy, so you tend to form a cloud over it. So, on a damp day where moisture is not moving around, washing doesn't dry, but on a windy day, that vapour gets blown away. So anything that traps it will actually mean that nothing more can evaporate from it. No more surface particles can jump out. And that's where you tend to see the condensation happening. So a lid on a container will form condensation. A visor that people are wearing at the moment, that's going to form condensation, just because there is nowhere else for that moisture to go except to lose its energy by giving it to substances and forming back into liquid. Diffusion, similar process. Again, it's all to do with collisions, but the actual particles move around in a random direction until they end up wherever they end up. Not dissimilar to convection. It's just that convection has that upward direction. Okay, so main three methods that we're going to look at: conduction, convection, radiation. Let's be very specific on this. I know you did some at GCSE, but we'll add a little bit more. So all particles collide. Okay, so collisions increase generally with temperature, with energy. Okay, so that's a general statement, but that doesn't mean it's necessarily a good conductor or a bad conductor. Okay, from GCSE, that's all true. Good conductors tend to have free electrons, or have more free electrons, and because of that ability to actually have free moving little particles, then those can move around and take that energy much more easily. So those are your main conduction mechanism. Yeah. However, let's just say to carry or transport the kinetic energy, so they take the energy with it. And they're moving, so it's kinetic energy. However, the other thing to think about is hinted back up here, is when these collide, okay, some particles will gain energy, some will lose. So what you end up with is that faster particles, i.e. the more energetic ones, they will slow down, okay, and slower particles speed up. So you've got this constant interchange between the velocity of particles due to these collisions. And that was very, very visible in our animation, in our model, the model where it had ball bearings flying around like gas particles. Okay, you could see some jumping higher because they're being struck from behind and therefore going faster. That can be solids, liquids and gases. Particles convecting is got to be only liquids and gases. So anything that is not solid, to be honest, it's anything that we call is a fluid. So basically it's the expansion of the fluid itself when heated. Okay, so particles are moving around more, just the same as all the other methods, but because of this they space out if they are a fluid. So what do we mean by fluid? Well, that's liquids, that's gas, that's vapour, which is basically a wet gas, kind of semi in between these, it's all to do with pressure, and you can also have plasmas. So anywhere where it's not fixed in position, anything that's not a solid, you can get convection in. So because of that expansion, what you get is the density decreases, the density of not the particles but the gas as a whole, or the fluid as a whole. And so because it is less dense than surroundings, when we go back to what you looked at when we did pressure, you know that that creates upthrust. So just put in brackets from the surrounding particles, okay, or the surrounding substance. So just remind you, again, that takes us back to the second law of thermodynamics, in that if those are all going the same speed, no heat's going to travel, okay? Let's say overall, because some will always be going a little bit faster and slower than others, but energy will not travel if they're all moving around the same. If these are at the same density, because it's not expanded, i.e. they're at the same temperature, then again you're not going to get any motion going on. Okay. Now this last one is ever so slightly different. Radiation, we know now it's electromagnetic radiation, and of course electromagnetic radiation is really just a small group of, and as it's heat, it's infrared photons. And where do infrared photons come from? Any single atom that has energy, okay? Pretty much covers all of them, so it's not even talking about, oh, these ones are hotter than yours. You know, this substance is going to cool by radiation because it's the hottest. It's just infrared photons, which are emitted by all atoms which have energy. Okay, so we know that energy of a photon equals HF, so if you want the total energy, we shall put there, then that's just going to be equal the number of photons times by HF. Okay, so, sorry, that should be a capital N for the total number of photons given out times HF. And we can think about the inverse square law and so on. But all of those things are all down to particles and collisions creating forces. If they're not colliding, it's not going to transfer that energy. So doing work by any of these four methods, or radiation. So anything with energy will shed that energy outwards, okay, until it is the same as the surroundings, and therefore everything will stop moving. Heat will stay where it is if everything is at the same temperature. Okay.